Hello, everyone from Berlin, from the beautiful city of Berlin. Today, I'll have the pleasure to talk about probabilistic demand forecasting at scale. Just before we dive in, a small introduction on myself. I'm Hagop, a product scientist working currently at Zalando. So I've been building ML products for the last 5 years and working on forecasting topics for the last 2 years. I'm passionate about everything that touches data science, deep learning, green tea, cycling, and running. So if you're also passionate about any of these topics, feel free to contact me either via Discord or via LinkedIn, or let's just get in touch. Okay. So today's agenda is straightforward. We're gonna start by posing the problem of demand forecasting in e-commerce that I work in. Then we're gonna have a look at what type of covariates we can use for demand forecasting. We're gonna have a review of deterministic forecasting methods and their limitations. Then we're going to embrace together uncertainty with probabilistic modeling and end up by presenting a real industry workflow for training and serving forecasting models that is inspired by my team and my department's work. All right, so the problem of demand forecasting. The first thing that we need to say is that demand forecasting is a core input to logistics and planning, right? It is a core input for making decisions. We have several areas of applications. One major application is inventory optimization, right? Where we're interested in answering questions such as, what are my optimal inventory levels for my different SKUs or products? When I need to inbound to constantly replenish my stock, where to optimally allocate the inventory in my network of warehouses or in my network of stores. The second application is also related is capacity planning, right? All of these stores, warehouses work with real human beings, right? Hence, it's very important that we optimally plan the workforce so that they are able to process either the outbound or the inbound. And the third one that we can code is assortment planning, right? So we're interested in, at any given time, try to have let's say the most optimal assortment of products possible online using demand forecasting. Okay, so this is just like an exhaustive list of potential applications, but there are many others that can follow up, right? But these are very, very common, and these are the topics that my team handle on. So one of the biggest problem, not the only one, but one of the biggest problem in demand forecasting is the problem of uncertainty, right? There are so many unpredictable things that can impact demand. We can quote, for example, weather, right? Today it's snowing in Berlin. I'm pretty sure that demand for jackets increases suddenly. We can have customer tastes and preferences that change over time. We can have economical factors, just like we saw in 2022, where we had all type of lows and highs. Pandemics, again, not that far ago. Only 2 years ago, we had the industry being completely disrupted, where demand, got a positive boom, but still, we had, let's say, an unpredictable factor in the increase of demand. And also this year, unfortunately, more sad events such as war. We live in an uncertain world, and the only constant is change and uncertainty. It's a constraint that we can't exclude, or we can't, just eliminate. It's there, and we have to work with. Okay, so this is the context in which we're gonna tackle. All right. Before diving into the modeling problems, I want still, to kind of present the data that we can use to capture this uncertainty, and then go into the modeling. All right. So what type of covariates or features we can use? As it's a time series forecasting exercise, the first natural thing is to have temporal and lagged features, such as autoregressive features. Let's say this is demand at time t, then you can take demand at time minus t at time t minus 1, t minus 2, t minus 3, etc., etc., etc. This is up to you to determine how far you need to go based on the pattern of your data. Right? We can have temporal indicators. We can also have specific dates and events being encoded. We can have weather and economic features data. Example is observed weather since the start, or the forecasted weather for the future. We can have macroeconomic indicators. especially like in this specific time, this is very useful. We can have a look at, for example, the consumer confidence index, like the inflation of prices, unemployment rate, etc., etc., etc. We can also go into Google Trends, where we would try to catch, let's say, how trendy the industry level keywords are at the moment, how the competitors are performing on the clicks, how our brands categories, etc., 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 or other uncertainty factors, right? So such as reported COVID cases. The main key point here is that we have a lot of indicators around the weather and economic feature that do capture the environment in which we're in, right? And ideally the environment in which we want to have the demand forecasted. Okay. The third level is SQ and posting level features, right? Let's say you're interested in like the lowest level of fine-grained possible, which is the article level. So in this case, you can really go and take features such as the price. If you know in advance that certain discounts are going to be applied, then you take the discounts. You can take some SQ taxonomy indicators, such as clothes, jackets, winter jackets. You can take SQ characteristics like the size of the product, the color, the material composition, or you can even go a bit more crazy and you have creative features such as neural embeddings. You can take the images of your product. You can take the bottleneck features from that images. You can have the title or description represented via encoded vectors, etc., etc. And so there are many ways, many creative ways to catch the article representation, but also the environment in which you are, right? This is fairly simple. Now that you know we have the problem, the concept of uncertainty, the data, let's start with the first idea that we can come up with, which is using deterministic forecasting methods. And we're going to discuss why they're not fully ideal given what we just described, right? Okay, so deterministic forecasting is also called point fire forecasting, right? Where we're mainly interested in forecasting one value at any given time t in the future, right? So we only predict with one value. And this is most of the time the average expected demand, okay? To train the model, we use pointwise loss functions such as MSE. And here the literature is pretty large, or like we have a large set of models that you can apply. Like you can start with the classical methods, what we call like the statistical methods, such as ARIMA, exponential smoothing, or Prophet. You can go into more machine learning models, XGBoost, LightGBM, all the ones that you know. And very recently, where we have seen a big boom in the research and also in the application of them, deep learning models that are performing pretty well in this specific case. You can have the choice to either use covariance or not, depending on the model. And you can either do single shot or a recursive forecasting, right? The main point here is that deterministic forecasting is pretty used. It's pretty old. It's pretty well used. And you have let's say big literature in terms of choices to do there, right? But we wanted to discuss also about the limitations, right? Not only what it is, why this is not perfect, right? So let's play a game together to demonstrate the point that this is not yet fully ideal. Okay. Let's say we are interested in learning the demand for the specific shoes. Okay, like let's say you're Zalando, like you have shoes that you want to replenish, and you need to know the demand for that specific shoes. Okay. And I'd come and tell you, okay, like the demand for the specific shoes is going to be 5,000 units for next year. All right. Just have a look at that. Then suddenly I actually present you two different forecast distributions possible around that mean value, right? I actually tell you, hey, it is highly likely that the distribution around this average value that I provided you can follow one of these distributions, right? It can be more like this, it can be more Gaussian, or even here log, right? Logarithmic. Then the question here to you is really think about it is, if I give you the distribution around this mean average, would you consider this mean average in the same way, right? Would you take the same risk? Would you buy 5,000 for the next week, given that you can have one of these three possibles? Just think about it. Yeah. Well, if you are honest, the answer is no, right? Like we don't have the same information. Okay. If I give you this, you can be sure that the uncertainty around the distribution is low. Here it's a bit higher, And here we can have, like these bump in demand that can increase, like the rare event of sudden increase of demand is a bit more likelier, right? So the spread is higher. So the main key point from this slide is that if I give you the distribution, you're going to have, different way of approaching the average value. Okay. And that's exactly the point, right? If I only give you like a deterministic forecast, so let's say if I give you this mean value, right? Well, you're not gonna have any information about the noise. It tells you nothing about the noise, right? We don't know if we're in a high or low noise context. How confident are we around the forecast? How does the confidence evolve over time, right? Do we completely explode the confidence in 2 weeks, in 3 weeks, and 4 weeks? We have no idea, right? But if I simply give you like a value, it's very risky to take a decision on. And you're kind of navigating blindly, right? So the key main takeaway is that point-wise forecasting, right? So deterministic forecasting tells you just nothing about noise and uncertainty and its evolution over time. And given that what we have presented about the problem of forecasting there, that is basically swimming in uncertainty, well, it is natural to say that these methods are not necessarily adapted for it, right? Or they do not necessarily help you in the exercise of capturing uncertainty, okay? So this is where, we're gonna solve the problem. You can easily say, okay, I prefer to use the point-wise forecasting and not and forget about uncertainty. That's one way of seeing it. But it doesn't have to be like that, right? We don't have to, kind of drop the arms and, drop the game. We can, work with certainty, right? Well, this is how we can do it. We can do it with probabilistic modeling, and we can live with uncertainty. It's not fatalistic, right? It's not the end of the world. We can still take decisions and enable stochastic downstream applications. Okay, so just a reminder before we go into this. So what do we have, right? So what we want from the probabilistic modeling is get the level of noise at every forecast point t in the future. We want to know if it's low, if it's medium, or if it's high noise context. We want to also have the evolution of the noise over time, right? How does my noise evolve? And thanks to these two components, we will then be enabled to downstream stochastic applications, right? Such as inventory optimizations, where we do inject some uncertainty variables. Okay. If we recap this visually so that we're on the same page, what we basically have is we have past, let's say, targets, right? So your past observed values of your time series of your demand. We have observed inputs. Some of them are known inputs that we know for the future, but also for the past. One good example is forecasted demand. Forecasted weather data, right? So we know in the future. You can take these, so past data that we know, future data that we know or not. It can be continuous, it can be categorical, it can be static. We take all of these, we put in the model, right? And ideally what we want this model to output is this here, right? On the top right corner, what we want is to have point-wise forecast surrounded by their prediction intervals, right? And these prediction intervals are gonna come and help us in quantifying noise. They're gonna quantify the level of uncertainty, okay? So yeah, let's dive into it. What type of probabilistic forecasting methods we have there? We basically can split them into two big families. The first one is frequentist methods, right? And the second one is Bayesian methods. In the frequentist methods, we can code different ones. Three main big ones come up. First one is learning distribution parameters, learning quantiles, or conformal predictions, right? Today's presentation is going to be mainly about the two first points, so learning distribution parameters and learning quantiles. But I still wanted here to note conformal predictions because I think it's still very interesting. It's a very recent methodology applied to forecasting. But I don't want to cover it because I was actually pretty disappointed when I tried to have, let's say, clean implementation of the solution. So I do consider it, as rather still researchy and experimental. So not yet, let's say, easily usable. Okay, so I wanted to exclude that one so far. Hopefully, in the future, we will have some nice implementation that we can use. Okay. So the first method that is widely used, and we have a lot of libraries implementing it in a nice and neat way, is learning distribution parameters, right? What we want is for every time t for your forecast, we want to learn the parameter of the distribution and of the demands, right? So let's say we make the assumption that the distribution is a Gaussian one around that t, then we will need to learn the parameters mu and sigma, or if it's a Poisson distribution, we'll need to learn the parameter lambda, right? The way we do this is by maximizing log likelihood, so that we learn the parameters theta. And what we see in the industry is that the main method that's really employ this and work well and can scale are from deep learning methods, right? Just to quote you some, we have RNN Gaussian, RNN negative binomial, DPR. Some of them allow you to have it single shot or recursive forecasting. One recursive is DPR. I think it's pretty known and also often used as baseline. Yeah. And the main point, like the main difficulty of this is that, and it's pretty big assumption, is that you need to make assumptions around the distribution of your demand, right? That's a big take. If let's say you're forecasting limited number of time series, 10 or 20, and you can check, that okay, my distribution is Gaussian for most of them, then it's fine to use that. But if you have hundreds, thousands, if not hundreds of thousands of time series, right, that you want to forecast, while making the assumption that all of them would follow, like a normal distribution, is a pretty big take. If they do follow by, like by chance, then that's perfectly fine. But otherwise, I still, personally feel that it's a very strong take, right, and can be considered as, let's say, disadvantage, like in this case. All right. The second family, like the second way of doing it, is by not learning the parameters of the distribution anymore, but learning explicitly like the quantiles of the distribution in question, right? And the good advantage here is that you don't need anymore to make assumptions about the distribution, right? You don't need to assume that it's Gaussian, if it's following like a t-student, any type of distribution that you want. You just learn the quantiles of that underlying distribution, okay? Again, here there are different ways of doing it. In this case, it's I'm only presenting the explicit way of doing it, which is using what we call the pinball loss, where we basically compute the pinball loss here for each of the quantiles, and then we take, like the sum of the pinball loss for all of the different quantiles that we want to measure distribution. Okay. The good thing is that we have here again many methods that from both ML and deep learning that allow you to do it. So it's very straightforward and simple to do. Like the ML one that I love particularly are LightGBM and CatBoost. They are on top of being incredibly fast, they also made adding this feature very easy. You just specify the loss function as quantile, and you can learn all the quantiles that you want. It's incredibly smooth and nicely done there. The second method is already a bit more complicated, I would say. It's the family of deep learning, right, where you can have multi-linear perceptrons. You have RNN-MQ, for example, CNN-MQ as well, or the latest model, there is temporal fusion transformers, right? The main point is that you have different methods that do this, and it like really allows you to bypass this burden of assuming the distribution, right? The second point that I want to mention in comparison between these two methods is that when you're learning the quantiles during the inference time, it might be a bit slower because you'll have to do like a lot of sampling, right? Once you have your parameter of the distribution, you have to sample from that distribution, and that exercise can be a bit slow. So often what we see is that even if some of these big models are slower than the other ones for during training, what we see is that when we use the quantile laws for inference, they tend to be a bit quicker, right? So it's always a balance to have, which methods works best for you in terms of inference or prediction time or training time, right? It's dependent on every case, and it's really up to you like to define what's the best choice. What's the best choice there? Okay. And if we look at an example of how the quantum forecast work, this is from like the DART-TS, right? Like on a toy example, you can see that if we forecast, this is what we should have, right? Like we have the different top one like the first and then the 99th quantile, the 10th and the 90th quantile, right? So it gives you like this idea. You can have all the quantiles that you want, but it doesn't have to be these ones. So yeah, this is how it works. How to evaluate, right? Like we just presented the ways and the loss functions that you can train the model, but how can we go beyond the loss function and have some meaningful metrics? Well, there are here still two ways. The first way is, let's say, not the orthodox way. It's a bit of a hack, but still very useful. It's if you want to use point-wise metrics using the median prediction, right? Let's say you use either of the two previous methods. You just take the median prediction, right? And then you can use any classical point-wise forecasting metrics that you know. It can be the MIE, the SMAP, the MAP, or the WAPE. Here, I really wanted to insist on the WAPE. That is particularly useful for demand forecasting because it basically weights the prediction, like the error with respect to the scale, right? And like in demand where we might have a lot of zeros, having this weight of close to zero is very, very useful. We basically do not penalize values closer to zeros in the same way that we penalize values are much higher, right? So this is very useful. On top of, again, like if you use these, you can just take any of your probabilistic methods, and then you can still compare them against, let's say, the classical methods. So any naive baseline forecasting methods or the statistical ones such as ARIMA, exponential boosting, etc., etc. The second way here is a bit, let's say, cleaner, and the recommended way is to directly go and use probabilistic forecasting specific metrics. Here we can code two. The first one is the continuous strike probability score that can be seen as a generalization of MIE for probabilistic forecasting. Or the second one is cross entropy, right? And the cross entropy here, I really want to insist on this. It's particularly appreciated in inventory optimization and e-commerce because it really puts greater emphasis on raw events, right? Again, as we described, it is possible that your demand can be zero for most of the day, but then for some reason, because of discounts or festivity, your demand can really have this, this bump for let's say a couple of days. So this is what we call a rare event, and cross entropy really captures the performance on these type of data very well. So cross entropy and WAPE are something that you see very often on this type of data. So in e-commerce, right? So we presented like the methods, like the metrics, the loss function that you can use, and I really wanted to insist on the libraries that make your life easy and allow you like to implement all of these methods and metrics. We have a lot of them, and the list is growing over time, so that's very, very good. I just wanted like to quote some of the biggest one that I used and I really found very useful. We have .ts, Nixla, there is very new, ASCII-Time, Gluon TS, and PyTorch forecasting. My team is personally a fan of PyTorch forecasting. Yeah, it's really up to like to go and have a look at that. Most of the methods that I just described are implemented here, and yeah, they make your life very, very easy, and they are meant for production code, right? Not simply research or experimentation, but really production code. So feel free to have a look. I think it's pretty interesting there. Okay, and now the cherry on top of the cake, and also like to conclude, is how can we how can we build a pipeline that trains and predicts one of these probabilistic models, right? So in my team, we're gonna start with the data lake, right? This is where all of our data sits, all the demand data, all the stock data, all the weather, all the economic indicators, all of them sit in our data lake. The first thing is we get the features, right? We concatenate everything together. We put our nice data frame. We put the data frame onto S3. Once this is put on S3, then we trigger the training and the backtesting job that uses SageMaker and GPU clusters, right? This is nice because you can literally have several instances with several GPUs, so you can really speed up your training and your backtesting. And once their training is done, right, you just save your model artifacts into the SageMaker model registry or any other one that you prefer. And yeah, that's the training flow. Once we have the training flow, the inference flow is again the same. We do the same features. We put them in S3. We go and get the model that was saved in the model registry, and then we predict using SageMaker batch transform with CPUs, right? So there are two tricks here that really allows us like to scale to hundreds of thousands of time series. Is the first one during training is using like the GPU clusters. This really does accelerate, right? Either for ML or deep learning, this really does help you. It's a bit of, it can be a bit a barrier if you're new to that. But I must say, like the libraries have made it so easy that, most of the time you just have to do a plugin. One example is PyTorch forecasting that uses PyTorch Lightning under hood, and just setting up a cluster of GPUs is very, very easy, and synchronizing that is very smooth. The second trick is during inference. We basically by using SageMaker batch transform, we basically parallelize the process, right? Each time series become one API request, and all of our hundreds of time series, right, just go and hit the cluster, and each and does as many requests as you want, right? Just to give you an idea, we have for I think 150,000 time series, we can do the inference using a temporal fusion transformer in 45 minutes. 45 minutes every day is very very quick. The training obviously takes a bit more time than that, but the good point is that you don't have to train your models every day. You can train it, let's say, once a week, and then you can run your inference every day. So you can kind of have this benefit of balancing the speed of inference and the speed of training. Okay, so and at the end, obviously, the most important is that our forecasts go into Amazon and the stakeholders can access it. And this is the best because they are happy, and that makes me happy. So this was it. Thanks for attending. Super useful links before we pass the questions. Zalando, including my department, is recruiting, so please have a look at the jobs link that I put here. And you can contact me at any point on LinkedIn if you want to discuss or have any question, or you just want to follow up on the presentation that I did. Please feel free to contact me. That's it.
Hello, Hagop. Was a great session and very insightful as well. Thank you very much for that. So we've got one question from Milano. What are the business applications? What business applications are you trying to solve? What are the counterfactuals you want to answer?
Yeah, so good question. So the business applications in my team are based to logistics, right? Where we have basically what I just put into the slides. If you remember, these were the ones here, right? So inventory optimization, capacity planning, and also assortment planning. These are the problems that my department has to solve, right? And the biggest ones are these two here, because having an optimal inventory replenishment policy is crucial to having always the stock available, right? So you need to have the demand that is one input to this. Demand just goes into this, and then we have obviously downstream stochastic application that does the inventory optimization. That's another modeling process, but the demand serves as one of the core inputs there. And the second one is we can using demand forecasting directly, we can estimate the number of people that we need in the warehouses to process at any given time in the next months, right? These two are the biggest applications that we're trying to solve.
Oh, great. Thanks a lot for that. The next question is from Matt. Suggestions on where to learn more on the methodologies and all.
Suggestion to learn more on these methodologies? Yes, I think that's also a good question. There's one book that I always love to mention. It's the book from Nicolas van de Poet, that is Demand Forecasting for Supply Chains. It's a very nice book that has some good examples that basically balances theory and practical sides. So so let me show you the book on the screen. Nicolas van de Poet, and the book is yes, very good books about inventory optimization and demand forecasting. And let's see the book. Here you go. So data science for supply chain forecast. I think that's like a very good introduction book. And if you want, you have the best ways to read the research papers, try to understand the methodologies if you want, and just follow like the blog post on how to apply this on more practical use cases. So the book, the research papers, and the blog post for how to apply them. Very very classical.